Welcome to the first video in my new series about data structures and algorithms, or simply DSA. In this video we'll explore what DSA is and why it's important, and I'll give you a first look at some basic concepts. Understanding DSA is crucial because it's the backbone of computer science. So what exactly are data structures and algorithms? Let's break it down. A data structure is a way to store and organize data in a computer so that it can be used very efficiently. You can think of it like organizing files in a cabinet. If everything is in the right place, it's much easier to find what you might need later on. Examples for data structures are lists, trees, and graphs. And an algorithm, on the other hand, is like a set of instructions, for example a recipe that tells the computer how to perform a specific task. For instance, how would you sort a messy list of numbers in ascending order, or how would you search for a particular contact in your phone. These are all problems that algorithms help us to solve. First, let's look at some common types of data structures. On one hand, we have the list. A list stores items in a specific sequence, and you can access them quickly by using an index, kind of like a numbered row of seeds in a feeder. A singly linked list, for example, would look like this. Each box is called a node and it contains two parts. One part stores a data value, and the other part stores a pointer to the next node in the list. The list begins with a reference called head, which points to the first node. And the first node contains the value Marie, the second node contains Alice, and the third node contains Leo. Also the last node points to null, which basically indicates us the end of the list. The arrows labeled next show us the direction in which the list is traversed. So this structure allows for efficient insertion and deletion of elements, especially at the beginning of the list. Next we have the trees. Unlike lists, trees are hierarchical. You can think of a family tree where each person might have parents and children. Trees are very useful when dealing with data that naturally forms a hierarchy, such as a file directory system. And finally we have graphs, which are perfect for representing complex relationships. A graph consists of nodes connected by edges. A great example of a graph is a social network like Facebook, where people are connected by friendships. So in this case the nodes represent the people and the edges represent the friendships. Of course there are many more data structures like stacks, queues, or hash tables that we will also briefly look upon, but our main focus will be on these three. Now let's talk about algorithms. An algorithm is simply a step-by-step process to solve a specific problem. Just like cooking a recipe has clear steps, an algorithm also needs to be clear, finite, and executable by a computer. For example, imagine searching for someone's phone number in a phone book. One simple algorithm might involve checking each name in order until you find the right one. Or if the phone book is sorted alphabetically, you could use a faster algorithm, but we'll get to that shortly. A famous algorithm is the Euclidean algorithm for finding the greatest common divisor of two numbers. If one number is equal to 0, you can just return the other number. Otherwise, we check how many times the one number fits into the other number. For example, for 12 and 44. The first step we do is we check how many times 12 fits into 44. It fits 3 times, leaving a remainder of 8. Next we apply the same process to 8 and 12, resulting in a remainder of 4. And then we repeat with 4 and 8, which gives us a remainder of 0. And at this point our algorithm is finished because we have reached 0. And the last non-zero remainder is 4, which means the GCD of 12 and 44 is 4. When it comes to searching, we have two common algorithms, sequential search and binary search. In a sequential search you simply check each item one by one until you find what you're looking for. So if we have a list F with n items, we iterate over all items in our list and check for each if the current item is equal to the searched one, and if we don't find it we return no key. If you wonder why we iterate from 0 to n minus 1, the first index of a list is 0 and n is the number of the items. So because we start by 0 we only have to go to n minus 1. This algorithm works fine for small lists, but for larger datasets it's pretty slow. Imagine searching for a list of 1 million items. You might have to check up to all 1 million items until you find the right element. So this type of search has linear time complexity, or big O of n. But we'll take a closer look at the time complexity of algorithms and what the O notation means. But we can already look at the best, average, and worst case of this algorithm. So we have basically the best case if the first element is the one we're looking for. In this case we have a running time of 1 because we only have to check one item. The average case takes us a running time of n plus 1 divided by 2, because on average the item we're looking for is in the middle of the list. And we have the worst case if the element we're looking for is at the end of the list, which gives us a running time of n. Now there's a faster option called binary search, which is based on the divide and conquer strategy. The only requirement for binary search is that our data is sorted. Sequential search on the other hand can also be used on unsorted data. Binary search can either be implemented recursive or iterative, but they both basically work in the same way. So here's how it works. We have a list and we search for the element 7. We have a lower border, which is our first element at the index 0. In this case it's the element 1. And an upper border, which is our last element, in this case 9. First we start by calculating the middle element. In this case our middle element is 4. If the middle element is smaller than the one we're looking for, we can eliminate the entire lower half of the list. And the same if the element is greater, we can eliminate the entire upper half. So in this case 4 is smaller than 7, so we can eliminate the entire lower half. This means our lower border is now 7 and 9 is still our upper border. We repeat the same process, so we calculate our middle element, which is 8. 8 is greater than 7, so we can eliminate the upper half. So now we have only 7 left, and that was also the element we were looking for. This cutting in half process makes this algorithm very fast. So now let's take a look at the time complexity of this algorithm. We have the best case if the element we're looking for is in the middle of the list. In this case we have a running time of 1. And for the average and worst case we have a running time of log 2n. Because in every iteration we divide our list in half. So this gives us a general logarithmic time complexity, or big O of log n. So you can see in general the binary search is way faster than the sequential search. For example, if we have 1 million items, binary search needs an average of 20 iterations, while sequential search needs an average of 500,000 iterations. But of course there can also be cases where sequential search is more efficient, for example for small lists or if our list is not sorted. To recap this video, we introduced the basic concepts of data structures and algorithms. Data structures help us to organize and manage data, while algorithms give us step-by-step instructions to solve problems efficiently. We also compared two search algorithms, sequential search and binary search, and saw how efficiency matters, especially when dealing with large data sets. And in the next video we'll dive deeper into some data structures, like lists, arrays, stacks and queues. See you there and thanks for watching.